Okay, let's move on to the next section that talks about matrix multiplication. And we'll define matrix multiplication actually in terms of work that we've done previously with regard to matrix vector multiplication and then also transformation. So consider the transformation TB of x, which we can represent by matrix multiplication bx, and let's say this is a transformation from a k-dimensional space onto an n-dimensional space, which would mean that x is actually k by 1. B has to be n by k, and then so bx, then the result has to be an n-dimensional space, so it's n by 1, and that's what we would get it by doing this corresponding matrix multiplication of an n by k matrix times a k by 1 vector would give us an n by 1 result. Now let's consider another transformation defined by a matrix multiplication that transforms from n space to m space. Okay, so here y, which is an original vector space, has to be n by 1. A then would have to be m by n. And then so finally ay would have to be in m by 1. Okay, so we could think about what it means to actually do this double transformation, transform x from k to n space, and then do transformation A, which would take that corresponding bx vector, which is in n space, and then transform that to m space. So we could indicate that double transformation as TA applied to the transformation, the resulting transformation of transformation B on X. Okay, or alternate notation for this is a composition of transformations, which we indicate with a circle here, a small circle, and so this is the result of this composite transformation. It would transform a vector X, which was originally in k by 1 space, into m space, Rm, with the resulting transformation. Okay. Correspondingly, we can represent this as, in matrix form, bx gives us is equal to a vector. Multiply that by a, that would give us then a vector in Rm space. Okay, and with B written as its column vectors in column vector form, B1, B2, BK, then we know that Bx can be represented as, this was one of the forms we had for representing a matrix vector multiplication from last time, x2, b2 plus dot 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 plus xk times bk. Then a bx can be written as x1, which is just a constant, times a times b1 plus x2 times a times b2 plus dot 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 plus xk, again just the kth element of our original vector, a times bk. Or we can rewrite this as, notice each of these is a vector, so we could rewrite this as a b1, which is a vector, it's a matrix times a vector, a b2 dot 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 a bk So we form this matrix by its column vectors. Each column in this matrix is our matrix A times the corresponding column in B, and then times our original X vector. Okay. So we're actually going to take this to be the definition of matrix multiplication. So AB, the product of two matrices, can be found by multiplying the first matrix by each of the columns in the second matrix. Okay, so let's look at an example here. I'm going to mark off some space right here so I can do this little example to illustrate this technique. So let's say A is equal to the matrix 1, 2, 0, 1, and then B is the matrix 1, 0, 1, 1, 2, 0. Then I can find the product of these two matrices. It corresponds to two successive transformations. I get the first column by multiplying the matrix A times the first column of B. So let me think about just this first column. I get the top element. It's going to be 1, 2 times 1, 0. So that would be 1. And I get the second element of that column vector by multiplying 0, 1 times 1, 0. So I have 0 times 1 plus 1 times 0, or 0. Similarly, I get the second column. It's 1, 2. It's the dot product of 1, 2, and 1, 1. So it's going to be 1 times 1 plus 2 times 1, or 3. And then 0, 1 times 1, 1 would be 1. So this is the second column. And then finally for the third column, it's 1, 2 times 2, 0. That's 2 here. And then 0, 1 times 2, 0. That's 0 there. Okay. And so this is a way to multiply two matrices. There's an alternate definition for matrix multiplication, an alternate way to find the product of two matrices, and this is probably what you're used to from high school. The IJ entry of the AB product is the dot product of row I of A with column J of B. And this is handy because it actually allows us to find any particular entry of the product matrix. So to get this element, say that the 2, 2 element here, I would actually take the dot product of the second row of A times the second column of B. So again, 0 times 1 is 0, plus 1 times 1 is 1. Similarly, for this element, the 1, 3 element, I would take the first row of A times the third column, 1 times 2 plus 0 to get that. So it allows you to compute the elements of the corresponding product matrix individually instead of computing the product matrix as columns. There's one point I want to make about matrix multiplication. Okay, let me go on to the new board here. And that's with regard to compatibility for matrix multiplication. So if A is m by n and B is dimension j by k, AB exists only if n is equal to j. These two inner dimensions here have to be exactly the same. And the result, and AB will be of size or dimension m by k. That inner dimension has to disappear. So if I take AB, let's say this might be 10 by 5. Okay. Then B would have to be 5 by something. Let's say it's 5 by 15. Then the resulting matrix would be actually of dimension 10 by 15. Okay. So this inner dimension has to be the same in order for the multiplication to even be defined. Okay, it's said that if that's the case, the inner dimension is the same. Doesn't matter what the outer dimensions are here. The first dimension of the first matrix and the second dimension of the second matrix. Doesn't matter what those are, as long as the second dimension of the first matrix and the first dimension of the second matrix is the same, then the two matrices are compatible for multiplication. And if that's not the case, then the matrix multiplication is not even defined. So if that is true, we say that A and B are compatible for multiplication. We had a requirement for addition for A and B to be compatible for dimension. For addition, the first dimensions have to be the same, and then their second dimensions have to be the same. In other words, A and B both have to be m by n. And so from now on, whenever I write AB or talk about an AB product, it will be assumed that they are compatible for matrix multiplication. Okay, let me talk about, before we talk about the properties of matrix multiplication, I want to define the identity matrix. I think I've talked about this previously, perhaps just for the 2 by 2 case. We generally denote the identity matrix by capital letter I. The identity matrix has just ones along the diagonal and then zeros everywhere else. Okay. So just ones along the diagonal. And then the identity matrix is always square, so it's 4 by 4 or 10 by 10, but it can be of any size. But it's always the identity matrix is always square, and it has the special property that A times I is equal to A, and then I times A is also equal to A. So let me list some of the properties of matrix multiplication, and that's actually the first property that I wanted to list. IA is equal to A. Now here A might be 10 by 3, in which case I would be 3 by 3, but the result would be 10 by 3. It would be identical to the original matrix. And then similarly, IA is equal to A. Now again, if A is 10 by 3, this time the identity matrix would not be the same as it was here. I, in this case, would have to be a 10 by 10 matrix to be compatible for multiplication, but 10 by 10 times a 10 by 3 would still give me a 10 by 3 matrix. So this is one property. A second property is that matrix multiplication is associative. A times, here we're talking about a triple product of matrices. A times BC would be the same as if we formed the AB product first and then multiplied that by C. This would be the associative property of matrix multiplication. Okay. And there's a distributive property across addition. A times B plus C is equal to AB plus AC. Okay. This is for left multiplication by A. Similarly, there's another one for right multiplication, this would be BA plus CA. And then fifth property here is multiplication by a scalar. K times K is the real number times the matrix product AB. That's equal to KA times B, or A times KB. So we can do the product multiplied by K, or multiply any one of the individual matrices by K, and then do the product. Okay, and then the last one is the transform of a product is equal to the product, transpose of a product is equal to the product of the transposes in reverse order. So that's key to remembering this. AB transpose is equal to B transpose times A transpose. And you can verify that if AB is compatible for multiplication, then BA is also compatible for multiplication. Now, one important property here that is not listed because it's not a property is that in general, AB is not equal to BA. In other words, matrix multiplication is not commutative. Now, this is true in some very special cases. It does require that the matrices actually be square for it to be true, but even then it's not true in general. A and B have to satisfy some very special conditions. You know, if A is square and then B is the identity matrix, then of course it's true in that case, but that's the exception. So this is a common mistake actually that students, when first solving matrix algebra problems, make. They'll make this assumption that matrix addition is commutative, and it is not. So left multiplication by matrix, left multiplication of B by A is not the same as right multiplication of B by A in general. So let me look at an example. This is an exercise from the end of this section using these properties. So this is exercise 2.3.16a, where we're asked to simplify this matrix algebraic expression, A times 3b plus C plus A minus 2b times C plus 2b times C plus 2a. Okay. First, kind of distribute this product across the sum, and then also use this property that I can pull a constant out front. So distributing A across the sum, I can write this as 3AB. And then notice here, I'm being careful that here A is left multiplying this sum, right? So I can't write this as 3BA. That would be incorrect. I have to continue to left multiply. And then similarly here, C is right multiplying this sum. So when I distribute this through, I get plus AC minus 2BC. And then finally here I get 2BC plus, it would be 4BA. Okay. Now in this case, did I write this down correctly? A 3b, and the original, it was actually a minus sign there and a minus sign here. So sorry about that. So I knew that because I knew these terms canceled out. I wrote down the problem incorrectly. So, but now I've got a minus AC plus AC. They sum to 0. Okay, and then here likewise I got minus 2BC and plus a 2BC, so they would sum to a 0 matrix. as well. Notice all of these matrices would have to have, these product matrices would have to have the same dimension. And so I'm left with 3AB plus 4BA as the result. Now you might be tempted to actually write that as 7AB or 7BA, but that would be incorrect. You can't simplify this any further because AB is not equal to BA. So this is the final result for this particular problem. Okay, I'm going to wrap up this video. There's one more video that I'll have for today's lecture. So there'll be three videos. I want to finish up this section on matrix multiplication. In the next video, we'll talk briefly about partitioning matrices so we can do block multiplication, and then also talk about another application of matrix multiplication using directed graphs.